Hello, my name is Caitlin Powell. I am a mechanical and aerospace engineering major from Oklahoma State University, and I am here to present my research on data collection for atmospheric soundings for gravity wave detection. The discovery of atmospheric gravity waves and their capability to transfer energy through the atmosphere has accelerated the interest in weather balloon soundings and the data collected to locate and characterize the generation. By examining the formation of gravity waves, which may be caused by wind shear, convection, or topography, one is able to get an improved understanding of how they might impact the atmospheric conditions, with the interest in using the information to improve weather and climate predictions. This research is focused on using weather balloons and radiosondes to take atmospheric readings while in flight. From sounding data taken at sunrise, the observations indicate that a production of gravity waves might be like those previously observed during a total solar eclipse. This presentation will discuss the experimental observation process and the methodology used to identify gravity waves of various types and how these observations are confirmed. We have put a focus of morning launches as a priority for our research because of the ideal conditions of having clear skies and still air. The research being conducted at Oklahoma State University is focused on looking at the impact of total solar eclipse on production of gravity waves. In addition to the eclipse, being able to identify the source of each gravity wave became important as it would further show the impact of an eclipse on the atmospheric phenomena. The team investigated 3 different sources of gravity waves and the ways to determine each gravity wave's origin. A test with the Oklahoma State team begins with setting up the ground station. We used the Luff WS302 UMB smart weather sensor, which gave us the local values of humidity, temperature, pressure, wind speed, and wind direction at the test site. These values were used for calibrating and initializing the radiosondes for flight. Once everything was set up and initialized, the launch configuration was ready to assemble. This assembly consists of a 30-gram helium balloon, connection line, derailleur, parachute, and radiosonde. The balloon's fill target was based off the total weight of the payload and the desired rise rate. For the most accurate data collection at a rise rate of 5 meters per second was targeted with a data collection every 2 seconds. Because we were looking at the effects of sunrise-generated gravity waves, a targeted launch time was scheduled in order to have the balloon at a specific altitude at the desired time. At this time, the balloon and the radiosonde were ready to launch and the data began to be collected. The flight performance of the helium balloon was that the balloon was expected to reach approximately 33,000 meters before it burst. This resulted in about 2 hours of data collected, where the flight would stop collecting data once the balloon burst. From the up-launch, further analysis of the collected data to identify, categorize, and verify the observation of gravity waves. The location that the Oklahoma State University team used as a test site is just outside of Stillwater in Glencoe, Oklahoma at OSU's Unmanned Aircraft Flight Station. This region and the area around it is very flat compared to other test sites in Montana and Kentucky, and would not produce as many gravity waves as a product of topography. This left the Oklahoma State team to focus on solar radiation and wind shear. In collaboration with other university teams, the researchers here at Oklahoma State University developed an app that would process the data collected during the atmospheric soundings. The image here shows the results of the wind shear detection, showing that the marked lines are the altitude at which high changes in wind speed was detected. These can be compared to those of the altitudes where gravity waves were detected and determine whether or not that they were caused by wind shear. The main focus of the research here at Oklahoma State University was the use of the sunrise to look into the solar radiation generated gravity waves. We found special interest in the sunrise tests because we thought it would be most similar to those of the solar eclipse tests that are occurring in December. By familiarizing ourselves with the data collected from sunrise, we hope that it will better prepare us for analyzing the data from the solar eclipse. Now looking into some of the results of one of our sunrise tests, we see graphed here a full flight. This is graphing the UV wind vectors against altitude to show where in the flight gravity waves were detected. You can see where a gravity wave has been detected when there is a loop in the graph. This data was collected on August 20th and was launched just as sunrise at 10:15 UTC, 11:15 and 12. From this sunrise launch, the gravity waves were plotted showing the intrinsic frequency. You may notice that further into the morning, more gravity waves were detected and were able to be plotted to compare. This plots the gravity waves a little bit differently, showing that at each detection, which direction that the wind was propagating in order to show where the gravity wave was being taken. To supplement a question and answer, I have included a couple of questions to go over. Why the focus of sunrise for a potential source of gravity waves? We have focused on sunrise because it creates a pressure differential resulting in an east to west wind. These low-level jets can create a wind shear that can generate gravity waves, and with the arrival of the sun's radiation on the region of the sounding, we are interested in comparing this data to the total solar eclipse sounding. How can you determine what is a gravity wave in your atmospheric sounding data? We use two methods. In a method known as Hodograph Method, we use the U and V components of the wind that are plotted as a function of altitude, and we can look at the altitude ranges that produce an elliptical plot. The closer the plot fits an ellipse, the more confident we are in that it is a gravity wave. The second method that we look at is the Morelei wavelet transforms. The transforms request a specific set of criteria to be met and is not able to identify all the gravity waves in the soundings. The plots presented in this presentation were using the Hodograph method. How much data can you receive for one sounding? From our radio sondes, we receive data on the duration, pressure, temperature, humidity, wind speed, wind direction, latitude, longitude, altitude, geopotential altitude, dew point, rise rate, elevation, azimuth, range, and density. And what type of impact do gravity waves have? The information that we gain through our research will be shared to advance weather prediction models. Moving forward with this research, later this year, Oklahoma State University will have a team of researchers in Santiago, Chile, preparing for the total solar eclipse that will occur on December 14th. For this campaign, the team will be coordinating with researchers from different universities to collect atmospheric data. The campaign is being performed to look at the behavior of eclipse-generated gravity waves. In conclusion, this research has continued work planned for analysis to be conducted covering the data collected from the 2020 solar eclipse. Additionally, the information gained on the production and effects of gravity waves will be shared to help advance weather predictions, and all progress will be shared with future research endeavors. Thank you for watching my presentation. I hope you enjoyed it, and if you have any questions, please feel free to reach out to me in the email presented in the first slide.
Thank you, Caitlin. Hi, my name is Zach Yap. I will be discussing the analysis of gravity wave data from atmospheric soundings. We will be going over the process of comparing atmospheric background reading data to recorded gravity wave data from a sounding. More specifically, we will be going through the process of identifying gravity waves detected from a launch we at Oklahoma State did earlier this year in August. So to gather our gravity wave data, we did weather balloon launches on mornings with clear skies and still winds. We did 3 launches, one an hour before sunrise to get good baseline data, one during sunrise, and one right after sunrise. Now, the first thing we did once we get that data back in the lab is we put it into some software we developed. The first thing we do is we plot the U and V components of the wind during the entire flight. We do this so that we can get a range of altitudes where we would expect to find gravity waves. And so that once we have these ranges of altitude, we can try to plot some hodographs. We plot these hodographs again based on the U and V components of the wind. And we are looking for plots that are very elliptic, because gravity waves tend to present themselves in elliptic hodograph plots. Another thing we can get from these right now while we're doing this step is we can also get the vertical propagation direction, so up and down. That we can tell based on the rotation of the hodograph as we plot it. Is it clockwise or counterclockwise? Once we have all these gravity waves detected, we can plot all of the hodographs at once, so we can just compare them. We can also get the detection altitudes and the propagation direction of each gravity wave. So the graph on the left will show the propagation direction. North is the upward arrow direction. Another thing we can get is the intrinsic frequency, which is denoted by the length of the arrows on the left, as well as that second line in the title. Another method that we use sometimes is the Morelei wavelet transform, in which we take the U and V components of the wind data and perform a Morelei wavelet transform. From this, we can find the maxima in the data and a few other parameters from the U and V components to determine the locations of possible gravity waves. And then we can analyze them a bit further using the Hodograph method. But this process is automated, taking a lot less time than the Hodograph. So for characterizing it, we use wind shear plots. And we're focused on wind shear plots in this case because we anticipate sunrise generated gravity waves to be caused by local wind shear. As the sun goes across east to west, it produces a pressure differential, which is anticipated to cause a east-west wind. And locations of max wind shear are denoted by those black lines in the graph. So how do we characterize gravity waves? Here we have two gravity waves that we've detected, and they are both quite elliptic, so we're pretty confident that they are gravity waves. And we can get an idea of their detection altitude. So this is 6 and 19. So 6 is detected about 19 kilometers and is moving in an easterly direction. And wave 19 is at about 25 kilometers moving in a westerly direction. And so if we look at our wind shear plots, we see that there is wind shear at about 18 kilometers up and another one at about 24 kilometers. And so that's within within a couple hundred meters of the wind shear. So we're fairly confident that those are gravity waves are generated by wind shear. But because we know that the wind is moving east to west, a sunrise generated gravity wave will most likely propagate in the easterly direction. So gravity wave 6, we can say with a little bit of confidence that is probably generated by a sunrise, while gravity wave 19 is probably not. So in conclusion, we need more data. Currently, we only have a small data set, and we have plans to continue to grow this data set by continuing to launch weather balloons. We anticipate getting more data to analyze this December as we have a team gearing up to take part in a campaign for the 2020 solar eclipse. Their focus is on eclipse generated gravity waves, but the process will still be very similar. Questions. Here are a few commonly asked questions that we have answers for.